Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying applications of first-order equations, specifically damped acceleration models. Let's take a look at Newton's second law. If you have a force F acting on an object that has mass m and is accelerating by a, then the force F equals the mass times the acceleration. If we let y of t be the displacement of an object, in other words, its position or distance from original starting position, then y prime is its velocity and y double prime is its acceleration. All of this is pretty standard stuff for anyone who's taken Calc 1. Now in metric units, people know that mass can be measured in kilograms and length can be measured in meters. If those are your units, the corresponding force unit is newtons. So if on F equals ma, if mass is kilograms, and acceleration is in meters per second squared, then your force is measured in newtons. If you're using centimeters and grams, so mass is in grams, not kilograms, and acceleration is in centimeters per second squared, then the unit of force is called a dyne. Now in imperial units, most people know to measure length in, say, feet, and force is actually the common unit of pounds. Mass in imperial units is actually measured in something called slugs. So we end up with a second-order differential equation. So the force is equal to the mass times the acceleration, and the acceleration is y double prime. So the force and the mass might depend on various things. It might depend on time. If you have a rocket ship, for example, as it burns fuel, its mass changes. Gravity could be decreasing as you get further away from a planet, so depending on your current height, the force of gravity might be different. With your velocity, you may encounter more air resistance, and perhaps that even depends on height because as you get higher in the atmosphere, the air gets thinner. So strictly speaking, our equation might look like this. The force might depend on time, it might depend on your height, and it might depend on your velocity. Okay, force could depend on time because your rocket is burning fuel at a variable rate, and at different times you're experiencing different forces. At different heights, you may have different air resistance. At different velocities, your air resistance might change. Also, the force of gravity might change at different heights, and your mass might be changing with time, and therefore your acceleration is probably varying with time. If we make some simplifying assumptions, however, we might be able to transform this into a first-order equation and solve it. So let's presume, for example, that the force does not depend on y, only on t and y prime. Okay, so our force, that could be something like gravity, isn't actually changing with height, and the force that we experience from something like air resistance isn't actually changing with height. Okay, so the force we experience might change with time because our rocket is burning fuel at varying rates, and it might change with velocity, okay, because the air resistance exerts a force generally proportional to the velocity or the velocity squared. But we're assuming that we don't have a dependence on height itself. That transforms the equation to be this. Force now no longer depends on y, only on t and y prime. And we always had mass possibly depending on time and acceleration depending on time. This can actually be reframed as a first-order differential equation. Instead of looking at the displacement y, look at the velocity v, because v is y prime and therefore v prime is y double prime. So we end up with this right here. Y double prime is just v prime, and y prime is v, so now we only have v and its first derivative. So we've reduced our situation to this first-order differential equation in terms of the velocity rather than the displacement. We're going to make a few more simplifying assumptions. For example, mass is not going to depend on time, and the forces are also not going to depend on time. The force F will still depend on the velocity. So mass is constant, but force only depends on velocity. For example, air resistance. We have a constant gravity, fine. We also have air resistance that depends in some way on the velocity, but it doesn't depend on time and it doesn't depend on your current acceleration. In this case, we end up with mv prime is just some force that depends on the velocity v. If we can solve this for the velocity v, perhaps we can integrate the velocity to recover the displacement function y. So let's take a look at a simple example to begin with. where we have an object of mass m and we drop it in a vacuum. In other words, there's not going to be any air resistance. So the only force acting on the object is gravity, which is now going to be constant because it only depends on mass, which is also set to be constant, but not velocity because there's no air resistance. So the force acting is gravity, which is going to be m times g, where g is the following constant depending on your choice of units: 9.8 meters per second squared, or 980 centimeters per second squared, or 32 feet per second squared. G, however, is the acceleration, not the force. Remember, force is mass times acceleration. So if you take this value of g and multiply it by the mass m, then you get the force. Assuming the initial height of the object is 200 meters, determine the time required to hit the ground. Okay, in other words, a height of 0 meters. So the mass m was not given, which means hopefully it doesn't matter. If the mass really affects the outcome and we weren't given it, it will remain in our solution as a variable. The heights are given in meters, so we're going to go ahead and use 9.8 meters per second squared. Okay, we are going to put a negative sign on our value of g because we do want our acceleration to be negative. We are being pulled down. So let's continue working through this simple example. So the differential equation has just become mass times acceleration is force, but our force was just mass times that gravitational constant. Now the masses cancel out, so v prime, our change in velocity, must just be g, and we were using negative 9.8 meters per second squared. We can pretty immediately integrate this to get our velocity as negative 9.8 t plus some constant. Our initial condition is that at time 0 we dropped, in other words we had no initial velocity. So we pretty quickly solved for c is equal to 0. Now that we know v of t is a nice explicit negative 9.8 t, we can integrate again to recover that y of t is negative 4.9 t squared plus some other constant. And we have initial conditions to find this constant as well. At time 0, we were at a height of 200 meters. So we just solved that if I plug in t equals 0, then y should be 200, and that immediately gives us that this constant c is just 200. So here is our function. Our height at time t is given by negative 4.9 t squared plus 200. Finding which positive times result in a height of 0 is now pretty much trivial. It's just a matter of applying the quadratic formula, if nothing else. And you'll quickly solve that t is approximately 6.39 seconds. So 6.39 seconds later, the object hits the ground. But now, let's suppose that an object also experiences another force, air resistance or drag. As the object moves through its medium, like air, it has to push air out of the way. And that air exerts a corresponding force on the object. So this is called a damping force. It's a force that acts in the opposite direction of the current motion. So whatever direction you're moving in, it acts in exactly the opposite direction. The force experienced depends on the velocity. The faster you move, the more air resistance you're going to experience. It also depends on the cross-sectional area in the direction of motion. If you have, for example, a needle moving through air, in the direction that it's pointing, it's going to experience very little air resistance compared to a big giant balloon. Just because it's bigger, it has to push more air out of the way. So the cross-sectional area in the direction of motion is also critical. Assuming the cross-sectional area remains constant, that our object is not changing shape as it moves, the drag is proportional either to the velocity or to the square of the velocity. These are the two most common scenarios to encounter. The distinction between the two possibilities of just drag proportional to velocity or velocity squared isn't really part of our consideration here. From an engineering or physics perspective, there are different scenarios for each. Generally, at low velocities, you're just going to be proportional to velocity, but for high velocities, it's going to be proportional to velocity squared. Exactly what counts as a low versus high velocity, not really our concern. We're just focused on the equations. Now we're going to take a look at something known as terminal velocity. Suppose you've got an object, its mass is m, but we're not dropping it in a vacuum, we're dropping it in some sort of atmosphere. Now gravity is going to be constant, and for convenience, we're going to round it off to 10 meters per second squared. However, since we're in an atmosphere, there's now a drag force. Okay, so we have to push air out of the way as we move, and the corresponding drag is going to be 5/4 times the velocity squared. Determine the velocity of the object at time t, and then what is the limit as t goes to infinity. So gravity is pushing the object down, So our force is going to have a negative 10 for gravity, but drag resists in the opposite direction, so that will be up. So we will have a positive 5/4 v squared. So on the one hand, our force is m times acceleration, or mv prime. On the other hand, it's drag 5/4 v squared with a positive direction, and gravity 10 with a negative direction. So we end up with mv prime is 5/4 v squared minus 10. We can factor the 5/4 out on the right and just get 5/4 times v squared minus 8. So here's our differential equation. mv prime is 5/4 v squared minus 8. We'd like to solve for v. But this is a separable equation. Okay, so we divide v squared minus 8 over to the left, and we're just going to put the constant m over on the right for convenience. Now we can integrate both sides. Okay, with partial fraction decomposition, v prime over v squared minus 8 is going to be adjusted into the following mess. 1 over 4 root 2, v prime over v minus 2 root 2, and the same minus 1 over 4 root 2, v prime over v plus 2 root 2. Notice that 2 root 2 is just the square root of 8. We're just factoring v squared minus 8 as a difference of two squares, v minus root 8 and v plus root 8. The partial fraction decomposition just works out as follows, but now we can pretty straightforwardly integrate both sides. So here's the differential equation we have after partial fraction decomposition. Integrating both sides, we just get 1 over 4 root 2 as this constant hanging around, log v minus 2 root 2 and log v plus 2 root 2. And on the right, we just get 5t over 4m plus an unknown constant. Combining the two logarithms into one term and multiplying the 4 root 2 over to the other side, we end up with the log of this ratio is 5 root 2 times t over m plus a constant c. We then exponentiate both sides, and as we typically do, e to the c gets pulled out as just some positive constant a. Here's what we've got so far. We have managed to isolate our function v, but it's in this ratio. V minus 2 root 2 over v plus 2 root 2 is a times this exponential term here. The only variable now is time t on the right. Assuming that the initial velocity is 0, because we did say that we were being dropped, well, if the initial velocity is 0, we plug in t equals 0, the exponential becomes 1. Here, if v is also 0, we get negative something over positive the same thing, and we just get a must be negative 1. So v minus 2 root 2 over v plus 2 root 2 must be negative 1 times that exponential. Now we can solve this for v. It takes a little bit of algebra, but you'll end up with v is 2 root 2 times this ratio of two different exponentials. So here's the solution we've got. The velocity is given by 2 root 2 times a ratio of two exponential terms. We can pretty quickly take a limit as t goes to infinity. Now, as t goes to infinity, both of these exponential terms go to infinity, but at exactly the same rate. So applying L'Hopital's rule, we'll see that the limit of this ratio is just negative 1. So the limit as t goes to infinity is just the nice constant negative 2 root 2. No matter how long you wait, no matter how much time you let go by, the velocity never quite reaches negative 2 root 2 meters per second. This is exactly the velocity at which gravity is exactly countered by drag. So remember that gravity was a nice constant negative 10, and drag was positive 5/4 v squared. Well, if my velocity is negative 2 root 2, then v squared is going to be exactly 8, and 5/4 times 8 is exactly 10. So this is the velocity at which drag and gravity exactly counter one another. So our velocity will gradually approach this, but never quite reach this speed. Now, gravity isn't quite constant, unfortunately. So gravity decreases according to the square of the distance between objects. So the gravitational force is some negative constant over y plus r squared. Where k is just some constant, the source of the gravitational pull, like the Earth, has radius r, and y is the height off the ground. So this denominator of y plus r represents your distance not to the Earth's surface, but the distance to the Earth's center, your height plus the radius of the Earth, for example. So this denominator squared is your distance to the center of the gravitational pull. K is still just some constant. But of course, force is mass times the gravity g. When y equals 0, in other words, at the Earth's surface, that allows us to solve by plugging in y equals 0. that negative mg should be negative k over r squared. In other words, k is mg r squared. So our accurate gravitational model says the force of gravity at a height of y meters, or feet or whatever, is given by negative mg r squared over y plus r squared. So we've determined that the force from gravity is given by negative mg r squared over y plus r squared. Force is also m times y double prime, so putting that in on the left, we can cancel the m from both sides. Y double prime is negative gr squared over y plus r squared. This is a second order equation. We've got y double prime, but there's some more trickery we can do here. The velocity is dy dt, but from the chain rule, if we tried to compute dv dy, it would be dv dt times dt dy. This is expressing v as a function of t and time as a function of y rather than the other way around. But dt dy is just 1 over dy dt, so we end up with dv dy is y double prime over v. In other words, y double prime is v times dv dy. dv dy is an odd term to show up here, but it's going to be very helpful to us. So far, we have the force is given by negative mgr squared over y plus r squared. By plugging, the force is mass times y double prime and canceling out the mass, we got this expression for y double prime, and we've determined that y double prime can be written as the velocity times this odd-looking derivative dv dy. So I put that in on the left, and we get v times dv dy is negative gr squared over y plus r squared. We can integrate both sides against dy. So on the one hand, we end up with the integral of v dv dy. That comes out to be v squared over 2. And on the right, if I integrate against dy, we get gr squared over y plus r. And we also have this constant of integration plus c. So here's what we've derived so far for our more accurate gravitational model. For the height y, the radius of the gravitational body r, and v, the velocity. Now let's suppose at time t0 we're at an initial height of y0 with velocity v0. So plugging in t equals 0 and replacing our height y and our velocity v with their initial values, we get this right here. This allows me to solve for c. It should be v naught squared over 2 minus gr squared over y naught plus r. Plugging that in for c, back in our original expression at the top of the page, we end up with the following. So we've arrived with the following expression. The velocity squared over 2 of our object is gr squared over y plus r plus v naught squared over 2 minus gr squared over y naught plus r. So we ask the question, is it possible to have a finite initial velocity that we never stop moving away from our object? So this is called an escape velocity. And we'll now determine if it exists, and if so, what is the value of this initial velocity. That means if we're, for example, on the surface of the Earth and we reach this v0, this initial velocity, even absent any other acceleration, we will simply fly away from the Earth forever. So here's the expression we have. Let's assume that v sub 0 is bigger than 0. So we begin by moving up. Assuming that y is bigger than or equal to 0 is always true, we always have some sort of height above the surface of the Earth. The first term is definitely always positive. Therefore, v squared over 2 is bigger than or equal to v naught squared over 2 minus gr squared over y naught plus r. If the first term here is always positive, then this is a positive number plus the other two. In other words, the left-hand side is bigger than just these two on their own. So we've determined that v squared over 2 should be at least as large as this quantity, under the assumption that our initial velocity is positive and our height is always positive. We can solve this and get v is bigger than or equal to this square root here. The plus or minus isn't really necessary. We're hoping that our velocity is always positive. So observe the term on the right is a constant. Okay, this v naught squared, g, r squared, and y naught, these are all constants. So the velocity is at least as large as all of this. If this constant is positive and our velocity began as positive, then not only is the velocity start as positive, it's always at least as large as a fixed constant. So if the velocity for all times is at least as large as a fixed constant, we are always moving up at least that fixed rate. So our velocity does not slow down to zero, and it certainly doesn't turn back around and hit negative values. Our velocity is at least as big as this fixed constant. We are always moving away with a minimum speed. So when the discriminant under that radical is positive, our object really will escape the gravitational pull and continue moving away with a minimum speed forever. This corresponds to our initial velocity being at least as large as the square root of 2g r squared over y naught plus r. So if our initial velocity is any larger than this constant, the object has a positive minimum upwards velocity for all time and flies away. Now, suppose you start at a height of 0. If y naught is 0, this simplifies a bit further. Okay, to just v naught must be larger than 2g over r. If I replace this with 0, I can cancel this r with one of those. So if you're starting from the surface of the Earth, and the Earth has radius r, and the gravitational pull is given by g here, if your initial velocity is at least this large, you're going to escape Earth and go off forever. On the other hand, what would happen if v naught was less than or equal to all of this? Well, by squaring both sides and moving that fraction to the other side, you'll end up with v naught squared over 2 minus gr squared over y naught plus r is less than or equal to 0. We're going to let c be some positive quantity so that all of this, which is less than or equal to 0, is written as negative c. Okay. Now this expression, v naught squared over 2 minus gr squared over y naught plus r, came up in our solution earlier. So we end up quite simply with v squared over 2 equals gr squared over y plus r, and then this constant minus c. Now c here is bigger than or equal to 0, so there's two possibilities. Maybe c is actually positive. Okay, now if c is positive, the velocity will actually be 0 if y takes a very specific value. Okay, if c is actually positive, then I can ask, when is the velocity 0? Set this equal to 0, move c to the other side, and solve for y, and you'll get this. Okay. So if c is actually positive, there is some value of y that will correspond to the velocity being 0. But if the velocity is 0, then we started moving up, and we eventually stopped at this height y sub m. After this point, since we have stopped moving, gravity is just going to start pulling us down. So this y sub m represents our maximum height. And notice that it's computed in terms of the radius of your gravitational body, gravity g, and this constant c, which also depended on your initial height and your initial velocity. In other words, based on a couple constants like the radius of your body and gravity, plus a known initial velocity and a known initial height, you can quickly compute your maximum height y sub n. After it reaches this height, when the velocity is 0, gravity will begin to pull it back down. So that takes care of the situation where c is actually positive. But what if c is exactly equal to 0? Well, this was our value for c, v naught squared over 2 minus gr squared over y naught plus r. If that's exactly 0, well, we had v squared over 2 is gr squared over y plus r minus c. But if c is 0, then I don't need to write it there, and I just have this. But assuming v begins positive, we did start moving up. Notice the term on the right is always positive. Okay, our y can't be negative, so this denominator is positive. Gr squared is a fixed positive constant. So v squared over 2 is always positive. That means v squared is always positive. And assuming our velocity is continuous, if it began positive and its squared is never 0, then I can't have negative velocity and I can't have 0 velocity. So our velocity v will remain positive for all time. That doesn't automatically imply that the object escapes to an infinite distance. It's possible to be moving up slower and slower and slower to never actually escape a fixed radius of distance. However, the only way that the velocity can approach 0 is as y approaches infinity. Okay, if I want velocity to actually get smaller and smaller, y, our height, has to get bigger and bigger and bigger. So the object does actually escape out to an infinite value of y, an infinite distance from our gravitational pull. However, it does so with a speed that asymptotically decreases to 0. So when this quantity c was positive, there was actually a fixed minimum velocity. Not only do we escape gravity, but our speed never drops below a fixed quantity. If c is exactly equal to 0, your velocity will asymptotically approach 0, but you do still escape to an infinite distance. Altogether, what have we seen here? Laws of motion regard forces. Forces are in terms of acceleration. That's a second derivative. So in theory, we have second order equations we need to work with. But we did see some scenarios where instead of a second order equation about y, we were able to get a first order equation about the velocity v, and then we could recover information about y after that. For example, if gravity is treated as constant, but there is a drag force from the medium, air resistance for example, there will be an asymptotic maximum velocity as t approaches infinity. There's some velocity at which the air resistance exactly counters the constant gravity. So as time goes to infinity, you approach but never quite reach this velocity. So that's called the terminal velocity, and it depends on the drag. Alternately, if we treat gravity more accurately as scaling with the square of the distance between two bodies, there is correspondingly an escape velocity, an initial velocity that if our object reaches that, it will escape away from the center of gravity forever with distance going to infinity. Below this velocity, there will, however, be a finite time at which you reach a maximum height, y sub m, and then fall back down.